In this video, we're going to talk about how to determine something that is called the formal charge on atoms in covalent compounds based on Lewis structures. So formal charge. What is formal charge? Formal charge is charge assigned to an atom in a molecule, assuming that the electrons are shared equally. Assuming electrons are shared equally. So that means that if we have a compound like, I don't know, CH4, and we draw the Lewis structure for it, we're saying that the electrons here, like in this bond, are shared equally between carbon and hydrogen. We're going to learn that they're not due to electronegativity, which is a measure of how badly atoms want to gain electrons and steal electrons. But formal charge is a cool little placeholder. It allows us to explain and predict which structures will be most stable in a Lewis structure, out of a bunch of different Lewis structures, based on this idea. So how do we calculate it? How do we calculate formal charge? So if you want to figure out the formal charge on an atom, remember we do this for every atom in a compound, and then for the compound as a whole. Formal charge is the number of valence electrons that that atom should have based on its location in the periodic table. So make a note of that. The number of valence electrons the atom should have based on its location in the periodic table minus the number of non-bonding electrons plus the number of bonds that atom has in the Lewis structure. Again, this is the number of valence electrons it should have from periodic table. And this is from structure. Now I'm going to do 3 example problems in this video to walk you through it. But first, before we do that, why is this actually important? What will this allow us to do? The cool thing about formal charge is it allows us to predict the likelihood of Lewis structures. It allows us to predict which Lewis structures, which I'm going to abbreviate LS, which Lewis structures will exist. Because some Lewis structures are possible based on the octet rule, but they're very unlikely to exist based on this idea of formal charge. So let's do some calculations with that formula that we said earlier. So example 1, H2O. So first thing we got to know how to do is draw the Lewis structure. So number 1, draw the Lewis structure. So for H2O, this would look like hydrogen bonded to oxygen with those 2 lone pairs around the oxygen. Each atom satisfies the octet rule. Each has a full valence shell. But now I want to calculate the formal charges. So let's say we just call this atom number 1. So if I want to calculate the formal charge of atom 1, I know that it's, if we look back at our equation, it's going to be the number of valence electrons that atom should have. So for hydrogen, the number of valence electrons it should have, so it's in group 1, so it has 1 electron, minus, if we go back here, the number of non-bonding electrons plus the number of bonds. Well, does this atom have any non-bonding electrons? Are there any just dots around it? No, so it's 0. Plus the number of bonds that that hydrogen has. Well, I just see 1 bond right here. So 0 plus 1. So this becomes 1 minus 1, so we would say the formal charge on that atom of hydrogen is 0. What about for this atom of hydrogen? I'm just going to label it 2 for tracking purposes. The formal charge of atom 2 here, again, the number of valence electrons it should have from the periodic table. Well, it's still hydrogen, so it's still in group 1. It should have 1, minus the number of non-bonding electrons plus the number of bonds. Again, there's no non-bonding electrons. There's no electrons that are just by themselves as dots. But there is 1 bond, so the formal charge for this atom is going to be 0. What about for the oxygen atom? I'll label as 3. Formal charge of 3. Well, how many electrons should oxygen have by itself based on where it is in the periodic table? It's in column 6, group 6A, so it should have 6 valence electrons. Now we need to think about how many non-bonding electrons does it have? 1, 2, 3, 4. Plus, how many bonds does it have? 1 there and 1 there. 2. So this would be 6 minus 6, which is equal to 0. You might be thinking, ooh, does it always have to be equal to 0? No, it doesn't. But if we go back to why is this important, we learned that formal charge allows us to predict which Lewis structure will exist. How do we know which Lewis structure will exist? It's the Lewis structure with the smallest formal charge. The smallest formal charges. Okay? So here, the total formal charge is 0. 0 plus 0 plus 0. So formal charge total is 0. And the formal charge on every atom is 0. So this is a very stable Lewis structure for H2O. What about CO2? So first step, draw the Lewis structure for CO2. CO2 would look like this. Boom. Boom. So let's do the same thing. Let's calculate the formal charge for each atom. So let's do it for this one first. So formal charge of atom 1, again, the number of electrons this atom should have is 6, oxygen, group 6, minus how many non-bonding electrons does it have? 1, 2, 3, 4, plus how many bonds does it have? It has 1 bond there, another bond right there. So 2 bonds. This does not count as 1 bond. It's one double bond, but there's 2 electrons participating in bonding, so that's why we put plus 2. So this is 6 minus 6, which is 0. What about for the other atom of oxygen, atom 2? Formal charge of atom 2, again, it's oxygen, so it should have 6 valence electrons minus 1, 2, 3, 4 non-bonding electrons, and 1, 2 bonds, 2 bonds to the atom, so 6 minus 6 is 0. And last but not least, what about this atom of carbon, atom 3? Fc of atom 3, well, carbon is in group 4, so it should have 4 valence electrons, minus how many non-bonding electrons does it have? Well, 0. There's no electrons by themselves. Plus, how many bonds does it have? 1, 2, 3, 4. 4 bonds, 4 lines touching it. So this would be 4 minus 4, which is equal to 0. Again, this is a nice stable structure because the total formal charge is equal to 0, and we've minimized the amount of formal charge on each atom. Each atom has a formal charge of 0. We'll talk about in class an example of a Lewis structure for CO2 that fits the octet rule, but does not have a formal charge that's this minimized. One last example. Cn minus, cyanide ion. Well, if we drew the cyanide ion, it would look like this. And I know that because carbon has 4 electrons, valence, nitrogen has 5, and then we have 1 here, so that equals 10 total. 2, 4, 5, 6, 7, excuse me, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But now let's talk about why this structure actually works. So let's calculate the formal charge on carbon. So formal charge on this carbon atom will be the number of valence electrons 4 it should have from the periodic table, minus how many non-bonding electrons, 1, 2, plus how many bonds, 1, 2, 3. So this comes out to 4 minus 5 equal to negative 1. So here's our first example of when the formal charge on an atom is not 0. And that's okay. It's okay. Our goal is to have them as close to 0 as possible. And we'll look at some examples where it can be positive in class. But that's what it is. What about for nitrogen? So on the second atom, formal charge on nitrogen. Well, how many electrons did nitrogen have? It's in group 5A on the periodic table, so it should have 5 valence electrons. Minus how many non-bonding? 1, 2. And how many bonds? 1, 2, 3 bonds touching it. So 5 minus 5 is equal to 0. Interesting. So now if we calculate the total formal charge Formal charge total would be -1 plus 0, which is -1. And do you see any connection between what the formal charge is and the overall charge on the atom, on the molecule, I should say? Cn minus is the same thing as Cn minus 1. And remember, we learned that this represents the charge on the whole compound. Well, how did we just prove that? Boom! The formal charge on the whole compound is -1. So there's a reason that those charges exist on polyatomic ions. It comes from formal charge calculations. We'll look at more examples with sulfate and nitrate and phosphate in class. But for now, what you need to know how to do is if I give you a Lewis structure or I give you a compound, you need to be able to draw the Lewis structure and then calculate the formal charge on every atom in that structure.